Stacy, here's a kind of interesting yellow powder. Put your finger in it.
Okay.
Now rub it together. Real slippery, isn't it?
Yeah, and it's real thin grains.
Very, very fine grains, yes. It's called lycopodium.
Lycopodium?
Lycopodium, that's the name of a moss, and this is the spore of the moss.
Oh.
And we're going to use it as a substitute for flour. So would you light the candle over there, please?
Okay.
And then put the burning match right into the lycopodium.
Oh, it went out?
Yes, it went out. Okay, now step back just a little bit.
Okay.
Because I'm now going to do this. Certainly flammable, isn't it?
Yeah. Well, if it's flammable, how come it didn't go out when you put it in there?
Okay, now think. What's the difference between the way it is now and when I sprinkle it over the candle?
Well, it's more concentrated there in the spoon.
Mm-hmm. And so each little grain doesn't have a good supply of oxygen.
Right, and you need lots of oxygen to have a good fire.
Okay, and when I sprinkle it over the flame?
You get a bigger flame because there's more oxygen.
Right. In fact, stand back. I'll give you a really good one.
Okay. Oh, neat.
Now, I said this was going to be a substitute for flour. Have you ever heard of flour mill explosions?
Yeah, I have in the paper and on the news.
Yeah, you see the tops blown right off and the
Yeah.
big fire and so forth. Well, that happens because dust, fine dust, which we're going to use this lycopodium to stand for, from corn or wheat or flour, fills the air inside, and then a slight spark of some kind gets it burning. So inside of this can, I have a funnel. See the funnel inside there?
Yeah.
Okay, I'm going to straighten it up so it's at the end of this tube.
Okay.
Okay, in the funnel then, I'm going to put some of that lycopodium powder.
Okay.
And at the other end of the tube, I will be able to blow.
And you're going to put the candle in with it?
Yes, I'm going to put the candle in with it. So we now have that entire can filled with very fine powder. So what should happen?
The top's going to blow off.
Yes. This is one you ought not to try at home unless your parents are around because you're using fire. Are you ready?
Yeah.
Would you like to blow?
No, you can do it.
Okay, here we go. So you see now why when they have flour mills or bakeries or wheat places where they store this grain, they make sure that all that little dust isn't in the air because you're certainly going to have a real good flour explosion. See, I have a simple pendulum here, Michael, attached to the swing, and a can full of pebbles. That's the weight.
Yeah.
What I'd like you to do, I'll start the pendulum here like this. You put your finger right there at
Touching
the back. Yeah, just touch it, but don't move your hand. Hold it very steady. Watch what happens when the pendulum comes back. Don't move it down.
It didn't come back and touch
It
me.
didn't come back. Why not? First of all, what are the forces involved in the pendulum?
Well, when you let go,
First of all, you put energy into it by raising it.
yeah,
Okay. Then when you let go,
the gravity pulls it down.
gravity pulls it down, right? And gravity pulls it down when it gets at the end of its swing over there, too, right?
Yeah, and then comes back.
But there are some other forces on it, too. It has to, after all, it has to go through the air.
So the friction of air?
Yes, the friction of air is going to slow it down a little bit. And also, the string might vibrate a little bit, especially up there at the top, where it's going back and forth. So there's a little friction in the threads. So with those two forces alone, the pendulum will never come back to where it started. Now hold your finger out again. You understand now?
Yeah.
Okay. Don't move your finger.
Didn't come back again.
You're sure of this theory now?
Yeah, I'm
Because
positive.
now we have the ultimate test. Come around over here and you hold it up like that.
But it might come back and hit my face.
No confidence, huh, in the theory? Just let it go and stand right there and don't move.
Okay.
Okay.
Let it go?
Go. Don't. You move. Come on. No confidence in the science at all. Now
Okay,
don't
stand
move this
still this
time.
time.
Don't move. There. In fact, you missed your face by about 3-4 inches. Anyway, that's kind of a nice fun thing to do because the pendulum can never come back up here because always some kinds of friction are working, and that's what makes the pendulum slow down. All summer long, these leaves were green because they contained chlorophyll, the green chemical that manufactures food for the tree. In the autumn, people see the changes in the leaves and they say they've changed or turned color, but that's not exactly accurate. When fall comes, the chlorophyll stops the food-making process and dies. The green color fades away, revealing the browns, purples, yellows, and reds that had actually been in the leaves but covered by the green all summer long. I assume you've heard that sound before.
Many times when the policemen go up our street or the firemen or the ambulance.
Right. Why do they use such a thing like that? You know what it's called, of course.
Yeah, it's called the siren.
Yeah. Why do they use a siren?
So everybody knows it's there because it's an awful sound.
Yeah, it's loud and makes a terrible noise. Well, have you ever taken one apart?
Nope.
Okay, well, let's do that. But before we do that, come over here so I can give you an idea how a siren works. See, here's a wheel that's full of holes. Mm-hmm. And notice the outside row are all nice and even.
Yeah.
So is the second, the third, the fourth are all nice and even row.
Yeah.
Except that row over there is not even.
No, all the holes are different.
Yeah, there's 2 there, and there's 5 here, 2, 3, 5. Now I'm going to turn it on, and then I want you to put that in your mouth, and then with the other end, you blow right into those holes, and hear what happens. Listen now. Just be careful now with your fingers. Okay. Wait a minute. Okay, try again. Okay, what did you hear?
I heard different noises,
Yeah.
different sounds.
What happens when the air comes out of this little tube and hits one of those holes?
It's cut into little pieces.
Right. As this goes around, it's chopping them into little pieces. Now, how about the sounds of the first 4 rows?
They were nice sounds.
Da, 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 right?
Scales.
Nice sound, sort of musical sound. That's almost the definition of a musical sound, in a regular sort of frequency, or regular sort of beat. Now, what happened when you went up there?
There was a yucky sound and it was all mixed together.
Yucky? Well, that's a pretty good description of it, yucky. Now, any time that you can break the sound, break air up into little tiny pieces, getting air, move it, break it into little pieces, and make those pieces irregular, you're going to get a yucky sound, as you say. Okay, let's go back and look at the siren now. We'll take the top off. When I turn it on, this little thing in the center is going to go around. Mm-hmm. Those are little fans in there, and they're going to blow the air out in all directions here through these holes.
Right.
So, watch.
The holes go bigger and smaller.
Yes, the holes go bigger and smaller. That means what kind of sound's going to come out of here?
A yucky sound.
Yeah, yucky. Constantly changing in frequency. And the faster you go, more the yuckier it gets. Okay, now, I'll hold it up don't back away. It won't bite you. Because I want you to feel that air is actually coming out of here. We'll break it up into little chunks, and you'll get an idea how a siren works. Are you ready? The guitar. Even though your favorite music group has been making new sounds with it, the instrument itself has been around since the 16th century. And in all that time, no one knew exactly why a guitar sounded like a guitar. Now, to make a sound, something has to vibrate. In this case, strings. But lots of instruments have strings, and they don't sound like a guitar. To find out why a guitar sounds like a guitar, scientists at Pennsylvania State University invented a new process called near-field acoustical holography. A grid of wires is suspended above the floor over a guitar. Hanging from the grid are 256 sensitive microphones like this one. The room itself is designed like a sound studio. Its walls, floor, and ceiling are covered with special materials to absorb sound. Dr. Julian Maynard makes final adjustments on the guitar. He invented this new system along with Dr. Earl Williams. The guitar is sitting on a platform a few inches under the microphones. Further adjustments can be made by remote control. As this motor turns, it turns the shaft, which moves all the microphones in relation to the guitar. A special device starts one of the strings vibrating, producing a typical guitar sound. The sound goes out in all directions, so the more microphones pick it up, the more information is recorded on which direction the sound came from. The signals from all the microphones go into this console. The Penn State scientists developed a computer program that displays how much sound was received by each of the 256 microphones. The map shows that most of the sound comes from the opening under the strings. Sound also came from a section near the bridge. Some also came from the neck, a finding that was somewhat unexpected. This work also led to the discovery that the back of the guitar acts something like a bellows to push the sound out through the opening. Near-field acoustic holography can be used to map other instruments to learn how to design them for more efficient sound production. The sounds of machines, even car engines, can be mapped to locate where the engine noise comes from. The result could be quieter engines. So after more than 500 years of use, scientists now know why a guitar sounds like a guitar, because they've mapped its sounds. Very good.
Thank you.
I think you will be a good experimenter because that's all I want you to do is blow out candles. And you look like you should be able to do that. I'll light it again. This time, all I ask you to do is to blow it out through a piece of wood.
Okay. I guess I'll try again.
Yes.
It won't go out.
Now, I want you to blow it out through a glass jar.
Well, I'll try, I guess.
All right. You did it.
Yeah.
How come you were able to blow it out through the glass jar, but not the piece of wood?
Well, I think it maybe was because the glass jar is round and the piece of wood is rectangular.
It's rectangular. In fact, I'll try blowing it out through the piece of wood. You watch what happens to the candle flame.
Okay.
What's happening to it?
The flame is being drawn toward the piece of wood.
Okay, what does that mean is happening to the air as it goes around?
It's circulating through, and when it hits the candle, the air goes towards
It's actually
the wood.
going this way. So it's
Yeah.
coming around here and going that way by the time it gets here.
Yeah.
Okay, now I'll do the same thing with the bottle, and you watch what happens to it.
Yeah, it's not going back towards the bottle, it's just going straight out.
That's because this is sort of, you said rounded. Have you ever heard of the word streamlined?
Yeah.
What does that mean?
It means so it's sort of rounded over the top.
Why do they streamline things?
So they can go faster and
Right,
move
so there's not as
faster.
much friction of the air.
Yeah.
Okay, now you did pretty well with that. Here's something for you to try on Chris. She likes to play tricks, right? This time you're going to blow out the candle through 3 bottles. Almost. Give it a... Wait, I'll move this in a little bit. Okay.
Okay.
Oh, almost. Try one more. You got it going. One more.
Okay, I'll try again.
Aha, you did it. I'll keep Okay, Billy, you stand right like that, and with one eye, look right straight ahead at those cards I have lined up over here. What do you see?
There is a King of Hearts in front of the Eight of Clubs.
You sure?
Yeah?
Okay, I'll put my hand in front of it, in between the two cards. Watch what happens.
It looked like the King of Hearts was in front of the Eight of Clubs. So really, it's behind.
Yes, when my hand gets there, you can see that it's behind, right? Mm-hmm. That's an optical illusion based on two things that you do in everyday life when you look at objects. Come on around here, I'll show you. First of all, you assumed that they were cards from a deck of cards, both the same size.
Yeah.
One of them looked smaller. Mm-hmm. Therefore, you said it must be further away.
Further away.
Well, the Eight of Clubs is not the same size. It's actually from one of those small decks.
Oh.
So I can put that in front. You'd still think that it was behind because it's smaller. Then the other thing is, when you see two objects and one of them covers up the other, what do you know about their relative positions?
The one that's being covered up is behind.
Must be behind, right. So in order to make that illusion, the corner of that card's been cut out.
Oh, so
that you can, when I had you line it up, I had you line up the corner of the king right with the corner of the cutout. So both of those things, the fact that one was smaller and you thought you could see one in front of the other, blocking it, made you think that the card positions were just reversed. Now go back there again. Now you know how to line it up. Yeah. You line it up with your eye.
Okay, it's lined up.
Okay, now, which one is in front?
The King of Hearts.
And which one's in front now?
The Eight of Clubs.
Very good. This may not look like a neon sign, but the principle involved is the same. Energy from a source, electricity in the case of a neon tube, and here from the sun, excites molecules. In a sign, there are molecules of neon gas. Here in the sky, there are molecules of gas in the air. The excited neon gas emits light to make the sign glow. The excited molecules in the air near the North Pole create the curtains of color you call the aurora borealis, or northern lights. Don't you have some real young people in your family someplace?
Yeah, I've got a couple of baby cousins.
Good. That will be the perfect age for a toy like this. I call it a comeback can. Watch what happens when I roll it down the desk.
It's coming back.
Mm-hmm.
Why?
Well, that's because of a scientific principle called potential and kinetic energy. Have you ever heard of those words?
Not really.
All right. Well, I'll show you what's going on inside there. It's relatively easy to make. But first, I want you to understand what potential and kinetic energy mean. The word potential means stored, and kinetic means moving. Set the mousetrap.
All right.
Now, when you pull back the spring like that, that's kinetic energy, the energy of motion. And now, when you get it stored in the spring, that's potential. Ooh, watch your finger. Mm-hmm. That's potential energy, the energy ready to go.
All right.
Okay, now how can you convert it back to kinetic energy, the energy of motion?
By setting it off?
Okay, you got the pencil, give it a... Okay, so we're transferring energy, both potential and kinetic, and back and forth all the time. So here's what you're doing with those two forms of energy inside the can. When you roll the can down the table, it's kinetic energy, right? The energy of motion. Look what happens inside.
There's part of a pipe and some elastic bands.
Mm-hmm. What happens when you push it and it goes down the table like this?
Well, the weight is probably heavier than the can and the elastic band, so it holds its place. Mm-hmm. But the elastic bands twist.
Right. And then what happens when it gets to the end of its run? You've stored the energy in the rubber bands, right? By twisting them up like you did in the spring of the mousetrap.
Well, the rubber band unwinds.
Unwinds, and that's what makes the can come back. Okay, so it's relatively easy to make out of a coffee can, some plastic tops, some matchsticks. Okay, give it a push. See how close you can come to the wall and watch it come back. see why I call it the comeback can.
I can't crush it.
Now, before you leave today, you're going to have the help of an invisible giant who, on your command, will squeeze it like that, just like nothing. Remember Aladdin and the magic lamp? Sort of thing?
Yeah.
Only this genie is going to be a real scientific one. Here's how we'll do it. See over here in the stove?
Oh, it's another one of those, except it's boiling.
Yeah. Blow on the top. See the steam coming out? Okay. Now, I'll turn the stove off so we get rid of the supply of heat, and I'll put this top on like that. Now, here, do you want to put on these padded gloves? Because I want you to take the can and put it over there in that tray in the place of the other one.
Okay. Oops.
Okay, I'll get the other one out of the way for you. Okay. Very good. Now that you've taken it off of the stove, what's going to happen to the steam inside?
Should go back into water, shouldn't it?
Yes. Okay, but now we've got it airtight so nothing can get in there. If the steam condenses back to water, what's going to fill up that space?
Nothing.
Yeah, it's going to be a partial vacuum. So you know who the invisible giant is that's going to crush the can for you?
Air pressure.
Air pressure, right. Already starting to work. Not quite yet, invisible giant, because you haven't commanded it yet.
Okay.
How could you make it go instantly?
By cooling it down somehow? With water?
First, command the invisible giant to squeeze the can and then pour the water.
Okay. Squeeze the can.
Invisible giant.
Invisible giant. Holy moly.
If you pay attention and want to try to repeat this, well, you better be sure that your teacher or your parents are around. Now, the reason it did that, 14.7 pounds of pressure per square inch is what air pressure is pushing. And if you can get rid of it, of course, all that pressure is there were probably tons of pressure pushing against here. Now we have a small problem in that it would be nice to get the can back up to where it was. And I'll take out the... See, there was still a little vacuum left, you hear it? Take out the hot water. Pour a little of the cold on it to make sure that the can is cool. And then what I'd like you to do is blow it up.
Blow it up?
Yeah, you've blown up a balloon, haven't you?
That isn't a balloon, though.
Well, go ahead and try it. Give a good puff. One more. You can get it all the way, I think. Very good. You're as strong as the invisible giant.